Hello. In this video we are going to look at a type of random process that does not have the Markov property. The particular stochastic process that we are going to look at is known as the inhomogeneous Poisson process. And by the end of this video, you should be able to explain the meaning of the term inhomogeneous in the context of stochastic processes. You should be able to explain how we could model inhomogeneous stochastic processes by using a time-dependent jump rate matrix Q of t, and you should be able to write out and solve the Kolmogorov forward equations for the inhomogeneous Poisson process. Before we get on to that, however, let's first of all quickly review what we have learned thus far about the regular Poisson process. When we introduced this random process, we talked about it in the context of this problem. We imagined sitting beside a single lane road, counting the number of cars that have passed. We said that cars would arrive at random times, but that most one car would pass by at any given instant in time because the road has only got a single lane. In other words, in our imagination, the random process looked like the animation shown here with the fish. We then discussed how this particular random process has a transition graph that looks like the one shown here, and further showed that the jump rate matrix for the Poisson process was given by the matrix Q shown here. With all this in place, we then solved the Kolmogorov equations and found that the number of events that occur during a time window of length t is a random variable taken from a Poisson distribution with parameter lambda t. In this video, we want to understand the inhomogeneous Poisson process. A good way to start developing this understanding is to ask the question illustrated here. In particular, we imagine having a Poisson process and ask the question, what is the probability that an event occurs in a time window of length delta t, shown here, and how does this probability compare with the probability that the event will occur in the earlier time window of length delta t, shown here? As it turns out, these two probabilities are the same, precisely because the Poisson process has the Markov property. If we consider the question that we started with, counting the number of cars that pass by along a road, this business of assuming that the events are uniformly distributed in time is not a particularly sensible one. After all, we know that on most roads there is a rush hour in the morning, as everyone goes to work, and a rush hour in the evening as everyone goes home from work. There will be much more traffic during these rush hours, and as such the probability that a car passes during the morning rush hour or evening rush hour will be much greater. Let's think about this again in a different way. Suppose that I have time on the x-axis of the graph, and the probability that an event occurs in a time interval of length delta t starting at time t on the y-axis here. Based on the logic that I have just explained, this probability will be low first thing in the morning before rush hour kicks off. When rush hour kicks off, the probability will then increase as the traffic becomes more heavy, as shown here. Once rush hour ends, however, the traffic will drop off again and fall to a much lower level, as shown here. It will remain at this lower level for most of the day, until the evening rush hour starts again. At this time, in the evening, the probability will increase once more, before finally dropping off at the end of rush hour. Given this, let's think about what happens to the expected number of cars that will have passed as the day progresses. If you look at the top graph, the probability that a car passes is constant before rush hour started. As such, the expected number of cars that pass by should increase linearly with time, as shown in the bottom graph. When rush hour starts, however, the gradient of this curve will increase. The reason this happens is that the probability that a car passes by in any instant in time increases during rush hour, so the gradient of the expectation will increase as we are expecting more cars to pass. Once rush hour ends, the rate at which the number of cars passes by drops off again, and as such, the rate of change of the expectation should also drop off, as shown on this slide. Let's now compare this behaviour with the behaviour that we observe for the average number of events in a Poisson process. We know that the expected number of events that have occurred increases linearly with time for a Poisson process. This is clearly not what we see for our traffic example, but it does give us a clue as to what we might do. We can introduce some time dependence in the lambda coefficient here. Think about this. If we do this, we can recover the behaviour of the curve that we have drawn for how the average number of cars that have passed changes as a function of time, as we would simply have a larger lambda parameter when we are within rush hours and a smaller lambda parameter when we are outside of rush hours. How then does this time-dependent lambda parameter manifest itself in the Kolmogorov equations? Well, it's simple. Now Q is not a matrix of real numbers. Instead, Q is a matrix of functions that depend on time. Remember that Q was the following matrix of limits, and we arbitrarily chose values for the limits that appeared in this matrix. In the Poisson case, we set all the n+1 elements equal to lambda. What I am thus suggesting is that instead of setting these limits equal to real numbers, we instead set these limits equal to functions that depend on t. For the inhomogeneous Poisson process, we thus have a jump rate matrix Q of t that looks like the one shown here, where, to reiterate, lambda of t is some function of time that is selected by the person who creates the model. Once we have this realization, the rest of this derivation proves to be relatively straightforward and similar to the derivation that we had for the Poisson process. We write out the matrices of the Kolmogorov equation on the last slide in full, and then we multiply the matrices on the right-hand side together to get the differential equations like those shown here. We get this equation by multiplying the first row of P of t by the first column of Q of t. We then get this equation by multiplying the first row of P of t by any of the other columns of Q of t. Let's now turn to the solutions of these differential equations. We begin with the first one of these two equations. As we have seen with previous differential equations of this type, our strategy here is to begin by rearranging the equations so that all the terms in P00 t are on the left-hand side and all the terms in t are on the right-hand side. We then integrate both sides. Now, as always, we are solving a first-order differential equation, so we need a boundary condition in order to generate a solution. The boundary condition we will use in this case tells us that at time 0, no events have occurred with certainty, and that as such we know that P00 of 0 is equal to 1. Also, notice that the upper limits in these two integrals are equal to P00 of t for the left-hand side and t for the right-hand side, and that as such we have written the integrands in terms of t prime. This is important. T prime and t are not equal. T prime is the variable we are integrating over in the right-hand side. Let's now actually do this integral. We cannot do the integral on the right-hand side as we do not know what the function lambda of t prime is equal to. As such, we cannot do anything to the right-hand side. For the left-hand side, though, we are integrating 1 over p00 of t prime with respect to dp00 of t prime, and this integral is just equal to the logarithm of p00 of t prime. Inserting the boundary conditions into the left-hand side, we get the following. Furthermore, the logarithm of 1 is 0, and thus the left-hand side is just the logarithm of p00 of t. We can thus get p00 of t by taking the exponential of both sides, as shown here. Let's now try to solve the differential equation for p01 of t shown here. Similarly to what we did for the regular Poisson process, the first step here is to rearrange the expression and put all terms in p01 of t onto the left-hand side. We then exploit the methods of integrating factors, as shown, and multiply all the terms by an integrating factor that is equal to the exponential of the integral between 0 and t of lambda t prime dt prime. Notice that in the resulting expression, we have a p00 of t multiplied by this integrating factor. Further note that we have just worked out that p00 of t is equal to the expression shown here. As such, the factor of p00 of t cancels with the integrating factor, and the right-hand side thus looks relatively simple. The next step in simplifying the left-hand side involves exploiting the product rule and the fundamental theorem of calculus. We can use these two facts to show that the left-hand side is equal to the following derivative of a product of functions. Remember, the fundamental theorem of calculus tells us that the derivative of an integral with respect to its upper limit is equal to the value of the integrand evaluated at the upper limit. In this case, the derivative of the integral between 0 and t of lambda t prime dt prime with respect to t is equal to lambda t. Pause the video now and see if you can use this fact to show that the derivative of the product shown at the center of the slide is equal to the left-hand side of the equation shown at the top of the slide. Now that you have confirmed that the step involving the product rule is valid, the rest of the problem is relatively straightforward. Just as we did when solving the previous differential equation, we rearrange and separate the variables. We then integrate and ensure that we use the boundary conditions we have been given to solve the problem. In this case, we know that at time t equals 0, no events have occurred, and that as such the probability one event will have occurred, p01 of t, at time t equals 0, we know that that is equal to 0. We now do the integral on the left-hand side and get the result shown here. As on the previous slide, we cannot do the integral on the right-hand side, as the integral here is written in terms of a function that we do not know, lambda t prime. The final result we get to is shown here. We can rearrange this expression by multiplying both sides by e to the power of minus the integral between 0 and t of lambda t prime dt prime to get the final result for p01 of t. We can continue this process to higher n values. What we will ultimately find is shown on this slide. The probability of 0 events is given by the uppermost equation, while the probability of n greater than 0 is given by the lower equation. In other words, the number of events that occurs during a time interval of length t for an inhomogeneous Poisson process is a random variable taken from a Poisson distribution with a parameter equal to the integral between 0 and t of lambda t prime dt prime. The inhomogeneous Poisson process thus gives us a way of modeling counting processes that do not have the Markov property. That is to say, we have a model that we can use to model the number of events that occur if the rate of change of probability that events will occur changes with time. With that then, let's just remind ourselves what the learning outcomes for this video were. Hopefully, having watched this video, you are now able to explain the meaning of the term inhomogeneous in the context of stochastic processes. You should be able to explain how we can model inhomogeneous stochastic processes by using a time-dependent jump rate matrix Q of t, and you should be able to write out and solve the Kolmogorov forward equations for the inhomogeneous Poisson process. If you think you can do these things, then you should be in a position to try some of the programming exercises and some of the paper and pen exercises on the inhomogeneous Poisson process. Thank you for your attention.